Hello students, this is Argen Kukitaev and we're going to talk about sampling from univariate distribution. Another word I could use instead of sampling would be generating random numbers. So it is sampling and generating random numbers are almost the same thing. And in the context in which we will use it in this course, these are the same things. So why do we need sampling? Well, I could say, well, for Monte Carlo, sometimes, right, we need to generate some random numbers to do certain things, and that's why we need to be able to generate random numbers, and that would be a lazy answer on my side, but I will give you a more interesting answer, which would be the following. As strange as it may sound, sometimes there are, or not sometimes, but very often in the practice of econometrics, we deal with probability distributions, the properties of which we do not, how would I say, we do not know, I should say, right? And but we somehow can generate numbers from these distributions, or as statisticians sometimes say, we can sample. So there are distributions from which we can sample, but other than that we don't know much about these distributions. So it sounds strange. How is it possible, right? So because so far we've been looking at the distributions such as normal, Bernoulli, and so on. We know everything about them, and I guess the question is, oh, how could we sample from them? And now I'm talking about the situation where it's pretty much reversed, right? We can sample, but we don't know much. How does this happen? I would say the most common example in the context of what we study, say financial econometrics, would be something called value at risk. So in the value at risk module, we study it in depth. Here I'll say the following. So suppose you have a portfolio of assets, whatever they are, stocks, maybe options, and if they're more complicated assets like options and some, credit default swaps, things like that, it's even better, right, to imagine. And so because then I may ask you the following. Well, tell me what is a quantile of the distributions of profits and losses of this portfolio. And when I ask it this way, it becomes clear that, well, but how do I know what's the probability distribution of the value of my portfolio? So it's not obvious. It's not immediately clear what is the probability distribution. But in this course we will learn the techniques with which we will be able to sample, we will be able to generate numbers from the probability distribution of value of the portfolio, of even a complex portfolio somehow. So without going into details, I'll just say that we will learn how to do it. And then having generated the numbers, possible profits and losses of this portfolio, we can learn the properties of this distribution, right? If you can generate a bunch of numbers from this distribution, we can look at the mean, we can look at the variance, and so on, and other moments. And we've learned, or at least I reminded you of this property of moments, is that if you know all the moments of the distribution, then you basically know the distribution. So we can study the distribution by studying the numbers coming from it. Right, so that was a long answer, but that is the, I would say, the main, that's the main application, the main use of sampling from univariate distribution, at least in my course, and it is also very, very common in the practice of quantitative analysis, let's say in financial services area or in econometrics and so on. So in this module we're going to look at a couple of things, themes. I would say we will look at pseudo-random number generators, and we will look at this particular one called RAND, which is available in Excel. and then we will look at the generation of arbitrary random numbers. So rand produces uniform random numbers, not only univariate but also uniform. So that's our plan for this module, and let's proceed. Okay, so let's look at this one particular univariate distribution, which is called uniform. Very easy, right? So what is a uniform distribution? It's such a distribution where I'm giving you, or you are given lower and upper bound, right? Let's say A lower band equal to 0 and B upper band is equal to 1. But A and B could be pretty much any number. So let's say it's 0 and 1. So in this case, what happens is that if I ask you to generate me 100 numbers, you will give me 100 numbers, and all these numbers will be equally likely to happen, right? So in other words, if we talk densities, right, the probability density distribution function is flat, it's just this flat line, and its height is actually 1 over b minus a. So if, for instance, if your lower bound is 0 and upper bound 1, then the density is 1 everywhere. So any number is equally likely in the interval between a and b. So that is what uniform distribution is, right? So density is flat. So density for all for any region between A and B is the same. That's why it's called uniform distribution. So we can study the properties of this uniform distribution, since we know its formula, using, let's say, calculus, right? So for instance, if I asked you what is the average, then it should be pretty obvious, even without any math, that the average is probably between A and B, right? A minus B, B minus A divided by 2. That must be the average, right? So it's pretty obvious. It should be right in between. So, and again, we remember what is the average or mean, right? It's an expectation of this form, where we take x, right, and then multiply it by the density, which we said if it's from 0 to 1, the density is equal to exactly 1. So we get the mean calculating this integral, and again, you can check it yourself, but it should be equal to 1/2, or b minus a divided by 2. So if a and b are not equal to 0 and 1, then it'll be a different number. Can be a different number, right? So in this case, okay, so we know the formula, so we could calculate it manually. On piece of paper, but at the same time, let's just see, we could study the mean by sampling, right? So we could get n numbers from uniform distribution and get the sample mean, x bar. And if we get n large enough, we remember from central limit theorem, right? It should, and law of large numbers too, right? So CLT, and we remember that if we keep increasing n, then x should be converging to the actual mean, which is 1 over 2. So let's say if we didn't know the actual mean, then what we would do, we would generate a lot of numbers x, and then just look at what is the mean is coming up with, right? So let's just do that. We'll do a couple of Excel examples. Okay, so I have the sheet I called uniform sampling. Right, so here I'm using rand function from Excel, but I don't have to, right? So let's not even use rand. Let's do something else. Let's go to Excel. There is data. In Excel there is data tab, and in there I have data analysis. If you don't have it, it's an add-in Excel. Please install it. So here we have this one of the add-ins. It's called random number generation. So let's just use it, right? So we will have, let's say we'll have a large number, maybe 10,000. So we'll have 10,000 random, excuse me, the first number is the variable. So we just need one variable, maybe, right? And then we will have 1,000 or 10,000 numbers of this variable. It says discrete. I want just uniform. I want uniform between 0 and 1. That's exactly what I want, right? And I'm going to just like output somewhere in the new sheet. I'm going to generate them. Oh, I forgot to fix the seed. So let's do it again, right? We'll go back and fix the seed because I want you to be able to reproduce exact numbers if you are interested. Let's give it a second. Is it still running? Yeah, it's still running. It's having trouble generating a lot of numbers, right? So well, I'm going to delete this whole thing, right? I'm going to generate it again. So we'll do the same thing, except I forgot to say we will fix the seed. I'll talk about the seed in a second. You will understand what I mean. So let's generate this again. 10,000 numbers in some sheet. I'll rename it so later you can pick it up and take a look at it, right? It's taking some time, as I said, not very fast in Excel. Actually, we can generate it much faster. You will see later when I'll show you how to do it using this technique called LCG, linear congruential. Okay, so we got the numbers, right? So I'm going to rename the sheet into uniform uniform 0, right? Meaning that the seed was 0. So this is 10,000 numbers, right? I hope it's 10,000. Let's check. It's 10,000. Great. So now, as I said, suppose I didn't know calculus and I didn't have Wikipedia and web browser to check what is the mean of the random of the uniform random, and I wanted to just test it, right? So just like study it. So let's see. Let's look at the average. So I'm going to look at the average, and the average is, let's see, average, right? So I'll take a whole 10,000 of them. Let's just fix it. Look, 0.5 something, right? Very close to 0.5. And remember, here, I just said that if I knew calculus, and I happen to know, then if I could calculate this, it would have been half. Now, let's study something else. As I said, we can study other moments. So let's study the variance. Okay. Well, we can write down the variance the following, and I'm writing these formulas down not for a reference really, but for you to get used to calculating expectations. So what is the variance? It's just an expectation of the squared variable, right? Probability weighted expectation. Well, you have to subtract the average, which you have to subtract the mean, and okay, we figured the mean is a half, right? So you do you write down this formula, and since density is exactly 1, I just skipped it. But you'll end up with this integral, and as I said earlier, and I can keep repeating it, it's not that important that you actually can take this integral. It's nice if you can. If you're a quant, you should be able to do it. But if you're an analyst, you don't need to be able to take the integral, but you need to understand what is this integral, and you need to be able to write it, and then something else or some other software or some other guy will take it for you. So we write down the integral like this, we take it, and believe it or not, the result is going to be 1 over 12. So let's say I didn't know that, right? And so I was given these numbers, and I just figured that I want to look at what's the variance. So let's look at the variance. For variance in Excel, again, there's a formula, right? It's called variance, sample variance. And there is sample and population. So I'm not going to go over definition which is which, but we're going to use sample variance because we we didn't get every possible realization of uniform numbers. We just got the sample, so we have to do the samples, not the population. Okay, 0.83 or something. So let us get a reciprocal of this, right? What is it? Close to 12, right? So it seems we're getting close to 12 as we wanted. So the idea here, which I was trying to show you, was the following: that if somehow we are able to generate the numbers or sample from a distribution, then we can study its properties, for instance, by looking at its moments, like mean, variance, kurtosis, skewness, and all that stuff, right? So we can do that. We can take some integrals like this. Well, I shouldn't have said that to confuse you, but basically what I'm saying is you can calculate a lot of different quantities using these numbers which you sampled, like moments and so on, and thus you can study this distribution. And that's exactly what we do when we apply Monte Carlo simulations to calculate some risk metrics of portfolios, of financial portfolios. Right, so if you hold some options and so on, there is a way to actually generate P&L. It's impossible to say what is the probability distribution of portfolio values, non-linear portfolios. Impossible to say, but it can be possible to sample from them. So that I know it may sound a little strange, but that's the reality. So when you can do that, then you do it. And in Monte Carlo, using Monte Carlo, you will study properties, risk metrics, expected returns, and things like that, right? So this was a demonstration of how do we study properties of the distribution using samples from them, right? So now let's talk about actual techniques. So we know, okay, well, good. It's good to be able to sample, right? We figured that. But now, how do we do it? So let's look at simple techniques or maybe practical techniques, right? And one of them is called PRNG. And we will look into detail of what is it exactly. This is pseudo-random number generators, and they're called pseudo-random for a reason. Even here, right, when I generated 10,000 numbers, remember I generated using some kind of a seed, right? So if I plug the same seed and generate these numbers again, I will get the same set of numbers. Strange, right? So what's going on here? If they were random, then how am I able to reproduce them? Well, they are not random, right? They are pseudo-random number generators. And in almost all, I would say financial, okay, in almost all cases where you would use it for, let's say, risk management and so on, you would use pseudo-random generators, not true randoms. We will talk about them in a second. So the thing about them being pseudo is that, like I said, they are not true random numbers, but, and contrary to that, they are not just not true random numbers, they are not random at all. They're completely deterministic. You can regenerate them as many times as you want if you are using the same seed. Yet they act like random numbers. You know, there is this saying in English, if it walks like a duck, quacks like a duck, and so on, then it's a duck. So we are sort of using the same idea here, is that when we generate the numbers using this PRNG, pseudo-random number generator, it's indistinguishable from random numbers in every aspect where we test. You can test it many different ways, it will always come back being indistinguishable from random. And since it's indistinguishable, let's use it, right? And again, I'll talk about two exceptions in the next slide. But here, let's look at one of the most popular choices of PRNGs, pseudo-random number generators. It's called LCG, linear congruential generator. Linear congruential generator, and I'm giving you the link to Wikipedia. It's pretty good in this case, so you can check it out. So how does it work? Well, surprisingly, it works according, look at this formula. This is all to it. All these random number generators you are using, including the one in Excel called rand, we'll look at it in a second, they are of something like this, right? Maybe not exactly like this, but very, very similar to this. Basically, in the core, they have this simple formula. So you get the previous random number multiplied by some number, add some other number c, right? And then you divide it by another number m, modulus, divide, we'll look at it, what is it? And that gives you a next number. So it's completely deterministic. If I know xn, and you can use it as a seed, right? If I know the first number, I know the whole entire sequence. Not only that, the sequence actually repeats. So if you run your random number long enough, at some point you'll hit the same number from which you started. Right? So these numbers, again, they are completely deterministic and they are cyclic. These are the cycles, right? But as I said, they act like if they were normal, like if they were truly random numbers. So LCG produces uniform random numbers. So remember, in the previous slide, we looked at the uniform distribution. So LCG is linear congruential generator. They produce uniform numbers, and we will see in a couple of slides later why it seems like why is everyone sort of trying to produce uniform random numbers. We will see it in a couple of slides later that actually once you have uniform, then you can get pretty much any other distribution. So that's why people focus on getting a very good uniform number, and from there on you can generate arbitrary PDFs, right? So let's take a look at this example. So is this the best random number? No, it's not. It's just like I pulled it from almost nostalgic reasons, right? It's very old. It's been used like in 80s, I guess, but it's surprisingly good and it's easy to implement. So let's just do that. So in the Excel, we will have we will have the sheet called LCG, right? So there's some comments in there. You can study it later in detail. Here I will just like walk you through the general idea, right? First of all, we have a seed. So what is the seed? Seed is the first number, right? So in this formula, right, for LCG, you have to start from somewhere, from like whatever is that very first number, and that's your seed. So you plug the seed. Then you plug it into this formula, right? You multiply by a, add c, and then divide by m modulus. And that is exactly what I'm doing here, and I'm using these numbers m, a, and c, right? So why don't we just even look at this? I think this popular number, right? Okay, we'll look at it later, I guess. But the idea here is that if you go to that Wikipedia page, you will find this exact set of numbers, M, A, and C, and you can read out on their history, like who came up with them, and so on. For us, it's not that interesting. Okay, someone used them. Let's try. So how are we going to do it? Well, so we're going to do it the following way. So our numbers are from 0 to 1, 3, whatever, minus 1, right? This m, they're going to, our numbers which we will generate will be between 0 and m minus 1, and m value is here. So let's see. My first column, A, is just number of observations. So where my first number starts, look at this. I'm using literally the formula. I'm using mod and mod modulus, right? So how does modulus work? Modulus is a remainder, basically, right? So you take three numbers, multiply and add them, and they will end up being, let's say, greater than m. In that case, you divide it by m, and whatever is the remainder, that's your modulus operator's output. So I just implemented this formula straight, and nothing special about it. I did the modulus formula, and I got this number, and as I said, the number is between what, 0 and m minus 1. So I have to divide it by m, and then I'll get the number between 0 and 1. That is my column C. If you look at my column C, all I'm doing is I'm taking the generated number and dividing it by m, and that's what all LCGs do, right? So these x numbers, big X numbers, they're between 0 and m minus 1, so you just divide them by n. So I got a bunch of numbers, and well, if you don't believe me that they're normal, that they're uniform, you do what? Well, you can try to do the same thing which I did. Let's just calculate the moments. So in this case, for you, I calculated the moments for 100 numbers, right? So maybe we can use other numbers. So we could use another C, 10, or they have to be positive. So some other number, right? It will change the whole sequence. No, I just calculated what I call here mean, and what is this, kurtosis, and so on. So we already know that the mean should be close to 0.5. So there's only 100 numbers, as it's not going to be exactly 0.5. And we know that the variance should be close to 1 over 12. And here I'm calculating 1 over 12. It should be 0.8333 and so on. So we got pretty close, not exact number, but pretty close, right? And then we will calculate skewness and kurtosis and so on. So for instance, if you calculate skewness, it's something like 0. And okay, I didn't talk about it here, but skewness of the uniform distribution should be 0, and we got pretty close to 0, and so on. You can calculate all the other moments and basically convince yourself that, oh, maybe these numbers are not, maybe these numbers are uniform. Well, uniform is good, but we want independent, right? We want independent numbers. So one thing you could do with this is the following. You could calculate the correlation, right? So let's calculate the correlation of what? Let's take a look at it. So here I'm calculating the correlation between what? First 99 numbers and then the numbers 2 through 100. So 1 through 99 and 2 through 100. What am I doing? I'm calculating the correlation between a number and the next going after it. Because look, we clearly are getting the next number from the previous one, right? xn plus 1 is a function of xn. But because of this modulus operation, it messes up the numbers so that although clearly they are not independent, look at the formula. Clearly xn plus 1 is not independent of x1. But if we calculate the correlation, it's not significant. Well, I guess you can check it whether it's significant or not, but it's very low, 0.22, right? So another thing you could do visually, and I do it quite often, is I do the scatter plot. So take a look at the scatter plot. So what am I doing here? Same thing. On x-axis, I get numbers from 1 through 99, right, of 100 numbers. But on y-axis, I get from 2 to 100. So that way, I'm doing a scatter plot of my next number as a function of the previous number, pretty much, right? So we could even look at what as the chart, right? We could look at and let's actually look at I don't see chart for some strange reason. I wanted to add the trend line, so let me see how to do it. Right, so let's look at the trend line, actually. Trend line with options. What can I do? Oh, wait a second, because okay, let's do it again. Trend line options, right? So we'll do the trend line, and we want to look at the r squared itself. So what is r squared here? Right, so r squared is very low. That's what you want to see. What you want to see, as I said, is the following, is that when you're regressing the next number on the previous number, r squared should be very, very low. It's sloped a little bit. It's always sloped, but the important part is r squared is very low, so there is no correlation there. So here I can actually say something here, right? So we clearly have dependent numbers, but they are not correlated, and that's an important distinction, right? So if you see correlation 0, it actually doesn't mean independence, unless it's certain other numbers. If you see, I mean, only in certain like specific situation. Generally, if you see correlation 0, correlation does not apply causation. So basically, correlation 0 doesn't mean independence. That's a teaching moment here, right? So that's what. So we saw how the LCG works, right? Now let's look at how RAND works. In the sheet with uniform 0, right, we studied uniforms which we got from Excel's random number generator, but we can sample them using RAND here. So right, let's see how many numbers I have. I have only 100 numbers, and I'm generating these numbers with Excel's RAND function. So you just call RAND and that will produce you a uniform random number. Then we can calculate again what mean, variance, and so on. And again, we're getting quite close, right? So unlike this uniform 0, which I generated with Excel's tools, and unlike the LCG, which I used, every time I press F9, look, my numbers are changing. Because RAND doesn't have a seed. Right, so RAND will just generate a different number every time. So if you're playing with RAND in your Excel simulations, keep that in mind. Reproducing can be quite difficult, right? Because you cannot fix the seed, so it's just a different set every time. Okay, so again, I hope I convinced you, right? So we can study the moments of the sample, right? And we could see that these moments are actually close to theoretical. So in column D here in the sheet uniform sampling, I set the theoretical numbers, what they should be if we had the full population. Obviously, every time I press F9, I get a different number, but you see they're kind of close. So it's quote unquote like proof. I'm like half jokingly saying it's a proof that it's normal. It's uniform numbers. But the point here is not that. The point here is I generated my numbers and now I can study the properties of the distribution by, for instance, looking at the moments. Okay, well, let's proceed. What's next? When we talk about LCGs, linear congruential generators, random number generators, pseudo-random number generators, I have to mention RANDO. So you, I hope, are all too young to remember this thing, but I probably, well, I actually missed it too, I think. I don't think in the software which I used when I was in college, I don't think RANDO was there anymore. But if I missed it, I missed it by just maybe a couple of years or so, right? So RANDO was a linear congruential generator, actually. So take a look at it's the same formula, right, which I showed you in the previous slide, except, well, it has some parameters. Well, the C was equal to 0, by the way, so it only had AX and mod M. What is it's known for is the following. People started using it, and they actually used it for a few years, I guess, until or before someone noticed something weird, right? So someone decided to maybe draw a 3D plot or 3D chart of these numbers. So it's similar to scatter plot, and except they used 3 numbers, let's say first, second, and third. And then they put them on X, Y, and Z axis, and then sampled, and then just drew them. So imagine that if you're just looking at 2 numbers, first and the second, right, next and the previous, then all these numbers, they will appear random on your screen on the plane. But when you do it in 3D, you clearly see all the numbers from this generator are on 15 planes. Is this random? Does this look random to you? No. Clearly not, like well, random, but not independent and not uncorrelated. So this is like a horrible sequence, right? And yeah, so this RANDO went into history as an extremely unlucky and bad pseudo-random number generator. So you have to be careful what you're using for, and I gave you the link. You can read about the history of this thing. I'll mention another thing. National Institute of Standards here, by the way, in Maryland. I believe their headquarters in Rockville or somewhere. So they have this battery of tests for testing random number generators, because it's extremely important in many fields, in science and so on, to have a good random number generator. So they have this battery of tests which you can download and use it if you created your own random number generator, and see whether they're good, right? So they test different aspects of random number generation. So this one wouldn't have passed it, right? Now let's talk about this interesting subject, somewhat related, or not somewhat, but clearly related, is the following. So pseudo-random number generators, which we looked at before, those even LCGs, right? They're good for pretty much almost everything you would ever use. I'm going to make that statement, or at least they were good for anything that I ever worked on. However, there are areas where some things are not, some of these generators maybe are not good enough, and these areas are tend to be related to, let's say, lotteries, gambling, but not only that, also to key generation in cryptography and communications and so on. So I'm not going to go into into details here, because it's not, how would I say, they're not, it's unlikely you would be working with these things, and I never worked with them, with these fields, right? But I had to mention. So in these cases, sometimes, right, people, for those applications, sometimes people use so-called true random numbers. We already said the ones which we looked are PRNGs, pseudo-random numbers, right? But there are some which I put quote-unquote true, right? But yeah, there's some numbers which are at least claimed to be true. They have their own problems. Read about them there. It's an interesting subject, but I'll mention two of them which I use them, but more like played with them. I didn't use them for actual work. So one is called random.org, and this one is based on radio noise. So imagine, like, sometimes not imagine, but if you ever use the radio and then you are tuning channels, sometimes between the channels you go and you hear, all you hear is some static, right? Some kind of a noise. So what these people do, they listen to the static, and then well, it's probably random. There's a lot of randomness going on, right? So there's a radioactivity coming to Earth atmosphere from sun, mostly from sun, right? And from other things, and then they all cause these, like, noise and so on. So they claim they're using that noise, and then their numbers are better, whatever, than pseudo-random. So that's one way. The other way is also interesting. There's this company called Hotbits, or a product called Hotbits. I gave you the link here. So their random generator is based on radioactivity, actually. So what's interesting about radioactivity is that you may or may not know, but you know, so what is radioactivity, right? So one kind of a radioactivity is when the nuclei of atoms decay. So let's say you have a piece of radioactive material, and while you keep it, while you're watching it, its nuclei inside, they decay, and when they decay, they emit something, and when you can actually detect whatever they're emitting. And if you count how many of them decayed in a given moment of time, that's a random number. So it's a random number, and there are these things called Geiger tubes, which can listen to radioactive decay. So it doesn't have to be nucleus; it could be some other radioactivity. But the point is that it's truly random. So the number of clicks you get is truly random. So let's take a look at this video very quickly. So I'm going to explain it once I'm able to copy it. I hope
sieverts per hour. FLIR identifying there are 440 can also be
right,
used
so
to identify
you will be
the
able
radioactive
to
material
actually go
giving
there
out the
and
radiation. Let's do that. The radionuclide identified
to watch
is
this video, right? So what is she doing here?
cesium-137.
Is she has this Geiger tube, right? And then she will go somewhere. Right.
Is in the soil. Let's check.
Right. So look at what she's doing. So when she put this thing, it starts clicking.
It is relatively high
noise,
at
right?
10 microsieverts per hour.
So that's what these random number generators do, right? So they they literally count the number of radioactive count the events of radioactivity, and these are random numbers, so you don't just plug them into a computer, you have to do something with them, but they process them, and on the output you will get the random numbers, right? So you need some software to work with these data and so on, but the idea is like these true random number generators, they're based on some physical processes. And then I put this video also for you as a reference. It's an interesting video on YouTube on generation of random numbers. So the guy talks about a few techniques and covers quite a bit. It's entertaining, and he also shows this Geiger tube approach. Right. So it's I can recommend. It's not required. Watching, but yeah, if you have time or you're interested, you could do it. Now we spoke about generating uniform random numbers, but what if you don't want uniform, or what if you want something else, like let's say Gaussian random numbers? So in this case there is this technique called inverse CDF, and this one is important, right? So make sure you understand this, because we will need it in the assignments and so on. So, and it's a very popular technique. So in a nutshell, it works like this. Let's say you want to generate some random numbers from a given distribution, and you know CDF of this distribution, cumulative distribution function. And let's say you can get an inverse of this CDF, inverse cumulative distribution function. If you can do that, then you can plug the uniform numbers into inverse CDF of your distribution, and on the output you will get the numbers from your distribution. So that's pretty much all of it. So let's look at details and then a couple of demos. So look at this. Suppose you have the CDF. I usually write it with capital F, right? Fx. What is a CDF? CDF is a probability that a random number will be less than a given number. So CDF of x means that your random number is less than x. What is the probability? So probability cannot be greater than 1 or less than 0. Right? So when x goes from left, like from minus infinity to infinity, your CDF f function should go from about 0 to 1, right? So when x becomes infinity, obviously probability that your x is less than infinity should be close to 1, or should be 1. So a CDF is a function where you plug your variable and you get a number between 0 and 1. Now, what is inverse CDF? It's an inverse function. So you clearly plug something between 0 and 1 and you get your variable back. So that's what's going on, right? So it's basically a transformation of your random number. And then now let's take a look at an example, right? So we will look at the following. CDF to uniform, right? So we are going to generate a bunch of normal random numbers. How? Well, we will go to data analysis, again, random number generation, but we won't do 10,000, let's just do 100, right? So we'll do 100 Gaussians, right? We could do anything, but we will use normal, why not? We'll use normal, standard, right? 0 mean, 1 variance, and we will again use the random seed. So let's just generate 100 numbers. Okay, here they are, right? We will call it CDF normal to uniform. So these are 100 normal random numbers. How do I know? Well, because I just generated them, right? Now, how do we convert them into uniform? Well, we do it the following way. We will apply the CDF, and this should produce what? It should produce normal. So let's see. There is a function norm sdist where we plug the normal number. It's a standard normal, and we will say it's a cumulative true. That's all, right? It's 100 numbers. Let's see. So for each number in column A, right, I produce some numbers U, and I'm claiming it's uniform. So let's see. Well, let's maybe look at the minimum of these numbers. Great. Well, almost zero. Seems not bad, right? So minimum is not bad. Let's look at the maximum. Max. Okay, close to 1, right? Seems reasonable. What about the mean? We already know that the average should be close to half, right? So let's look at the average. Close to half, right? Variance, we know it should be something like 0.0833, whatever, right? Let's see. Variance. Something happens to my Excel from time to time. Not average, variance, right? We need sample variance. Okay, not exactly 0.0833, but close enough, right? So I hope I convinced you. So when we apply CDF of the distribution function, CDF, cumulative distribution function, to the variable itself from this distribution, because CDF is a function. So when we apply function on a variable, we get a new variable, right? And that new variable just happens to be uniform if we are producing, if you were using the same CDF, right? So that's great, but it works the other way too. And actually, this fact that when we apply CDF to variable itself and then we get uniform, we will use it in one of the assignments, right? In the copy assignment. So let's go the other way. Let's produce some uniform random numbers. We will produce some uniform random numbers. Well, actually, we already have them. We have a lot of them. We have 10,000 of them, right? So are we going to use 10,000 of them here? Well, why not, right? So I'm going to write this as a uniform here. So some uniform numbers. But let's now try to produce a standard normal. So as I said, all we need to do is inverse. So let's look at norm S inverse. This is a norm, standard normal inverse CDF function, and we plug some numbers between 0 and 1. Okay, and I know we have 10,000 of them. Great. So how do we study this? Well, same way. So let's do it. So except here, our average should be of, we're getting average of these. 0, close to 0, right? And we know the variance should be close to 1 if these are normal numbers. Let's see. Oh, look, close to 1. But more interestingly, kurtosis, right? So we know kurtosis of normal distribution, well, in this case, it's excess kurtosis. It should be 0. Excess kurtosis, let's see. Okay, we're going to call the function called kurtosis in Excel. And again, kurtosis in Excel, kurt function, is excess kurtosis, almost 0. Now let's do the same thing for right? Kurtosis for our uniforms, and it should be like 1 over 1.2 or something like that. We know that, right? So it's like 1.2. So kurtosis of uniform distribution is negative, minus 1.2. Right, so I hope I proved it. I proved it to you that this inverse CDF seemed to be working. So what did we actually accomplish here? We accomplished something interesting. We said if somehow we know the inverse CDF of any distribution we want, we can produce random numbers from this distribution and uniform. So you run the uniform and then apply this distribution and get whatever you want. All right. What is the problem with this though? The problem with this is the following. I just showed you how to do it with Gaussian, and it seems to work, definitely works. The problem is it's slow. Right, so because the CDF, especially inverse CDF of normal distribution, is a relatively slow function. Well, we didn't notice it in Excel because we just had 100 numbers and these computers are very fast. It's fast enough for a lot of analysis work you would do. If you're not a quant, it probably is good enough. So you could apply this function which I just showed you just fine. It'll probably be fast enough for you. But if you're a quant and you're running some simulations, Monte Carlo and so on, you may quickly run into trouble with performance. It's too slow. Like it may sound strange, but yes, it can be too slow. So in this case, real statistical packages, they do not use this technique for normal distribution. So you can use this technique for, well, you will in many cases where you don't have any other choice. But in case of some distributions such as Gaussian, or normal distribution, it's so ubiquitous. You need it in a lot of places, like in quantitative finance, it's everywhere, right? Brownian motion and so on. So that people figured out how to produce this Gaussian or normal distribution much faster than using this inverse technique. And one of these techniques is called Muller transformation, Box-Muller. I'm going to look at two other techniques, which one of them will be even worse than this inverse technique, sampling normal with CLT. So let's think of how would you sample normal distribution with central limit theorem. All right. Think about this. Central limit theorem says literally the following. Right, so if you get the average of n numbers and then standardize it, meaning if you remove true mean and true sigma and multiply by square root of n, it should be normal, standard normal distribution. Right, what does it tell us? It tells us the following. If somehow I'm generating, let's say, and this works because of central limit theorem for any distribution. This x can be from anything. So you get the average of some random numbers and it'll be normal distribution. Right, so we saw that in CLT. So you can use that. So you can generate a bunch of random numbers. So let's say uniform. You could generate uniform. You generate a bunch of random numbers, uniform, and you know what's the mean and sigma of uniform. So you can apply this transformation, and on the output you should be getting normal distribution. So it sounds like you need to generate, like, I don't know, 10, 100, whatever uniform distributed numbers, and in the output you would be getting something like a normal distribution, right? So let's see how you could actually do it. So let's see. So we will do CLT random number, but we will do it the following way. So we'll go to, again, random number generation. Instead of normal, because we're trying to prove the point, we will use uniform. So let's generate 100 variables, so we will generate 100 columns with 10 rows, basically. That's what we're going to do. We'll use the seed 0 and so on, right? Let's do. So we will call the sheet, we will call it normal, we will call it Gauss with CLT, right? So what's the idea here? Well, we have 10 random numbers, they're uniform, and we're going to apply the formula which I just showed you, right? So we will do the following. We will get the average of these 10, because CLT wants average, and then we'll subtract the mean, and we know the mean is 0.5. Subtract the mean, and we will divide it by sigma, which is 1 over 12, and again, remembering this formula, we just have to multiply by square root of 12 and n, basically 120. Right, so now we need to multiply this by SQRT 120, and I hope I'm right. So we will have 100 of them. Right, so now we have these 100 numbers, and I'm claiming they should be like a standard normal. Well, how do I know? Again, we can do the same thing like before, right? So let's do the testing. We will do average, right? Average is going to be let's fix this. Well, not 0, but kind of close enough, right? So let's do all shebang, right? We'll do variance, we'll do skewness, and we will do excess kurtosis. So let's go ahead. Okay, this is going to be skewness, skew. This is going to be well, why skew? This should be variance. We wanted variance. We wanted variance close to 1, good, right? Skewness should be close to 0 if we're right. Well, close enough, right? And let's see kurtosis. Again, should be close to 0 for normal distribution. Excess kurtosis. Not exactly 0, but close enough, right? So it seems we could do it. Now the question is, should we be doing it, right? So is this dumb? Well, I would say in today's age, yes, it is kind of dumb, but that's how Monte Carlo actually works. So a lot of Monte Carlo is based on something like this, right? But if I'm just going to generate normal distribution, I wouldn't be doing this now. But guess what? Like long ago when I was in university, like in the past century, I actually did that. So I had the software where I had uniform, but I didn't have normal, and my advisor said, oh, just get like 10 uniforms and just get the average, it'll be normal. At that time I was I don't think I knew central limit theorem yet. I was already programming, but I didn't know stats, so I was kind of surprised, but in the end it looked like normal, right? So yeah, I did that. I will never do it again. It doesn't make any sense, right? Why? Because we have techniques which are much faster today. So for instance, Marsaglia. Even this one I will not be implementing, and you will not be implementing for real work. But these techniques, say this Marsaglia method, it's in software such as like in Python or some other languages. They're probably even using better techniques, but this kind of a technique can be used, and it actually is implemented in software. It's just you don't need to do it yourself anymore. I can show you a quick example how you could actually use it, right? So for instance, we could do this. Let's do Marsaglia, just for the sake of it, right? Okay, where are we? Marsaglia, right? So it seems all we need is some uniform random numbers, right? So we can actually generate. We already know we could do it with rand, right? So let's just do it. So we need a pair of uniform random numbers, and we'll just say rand here, and the other one is rand2, and maybe we'll generate a bunch of them, maybe 100. Okay. So the next is what we're going to do is we will just calculate these bunch of functions. So we will calculate this function called, not the function, but entity called s, right? So this one is a number we called it u, and the second was v. So let's do s. So s is a squared. sum plus v and squared. That's all to it. This is our s. Now we need to calculate two other numbers, z0 and z1. Right. So what is z0? All it does is basically this first number, uniform number, you multiply it by, and I'll fix it in a second. Multiply it by square root of this interesting quantity minus 2 multiplied by log of s, happens, right, of s, and divided by s. That was z0, right? So what's going on here? Well, because I said s, I should use the actual value. Excel doesn't understand that. Right, so I'll now I'll do the same thing for the next wait a second, for the next random number, but here we could see that it's positive and it's v. That's all the difference. So we don't need this minus, and this is going to be b. Right, so we got two numbers here, b2. What just happened? I messed something up. Must be negative 2 here. Minus, wait a second, what's going on here? Right, okay, yeah, so it seems to be working. So I just do that, then we need to test the condition. So your s should be between well, first of all, your the uniform, not between 0 and 1, but between -1 and 1. So how do we do that? We multiply by 2 and subtract 1. That's the way to get it from -1 to 1. Right, and so we did everything right, except now we need to put a test here. So the test here is that if this s number should be between 0 and 1, strictly between 0 and 1. It can be it should be greater than 0 and lesser than 1, right? So, and that's what we're going to test. We're going to test, we're going to say if and, right, that your s is greater than 0 and s is strictly less than 1. And if that's the case, then we can use this number. If that's not the case, we will not use the number. It'll be empty cell, right? So in this case, I'm using only one of these, right? So let's look at the other one. So here it's the same thing, except we want to use, instead of E2, we're going to use F2. So now we got two normal numbers. So these are normal numbers now. See, if s is greater than 1, then we're not using the numbers, right? So what we do is we put them here, right? And that's all. So we have a set of random numbers. Sometimes we have to reject and you just throw away this number. Unfortunately, this didn't work, this pair, but you just skip them. And whatever you didn't skip, these are your random numbers, right? And these are supposed to be random normals. And you can test them, look at the means, kurtosis, and all that stuff. But basically, Marsaglia method works works like this. So, and it's more efficient, this technique. There are, again, variations of it, like I said, Box-Mueller and so on, and I gave you a couple of references just to look at it if you are interested in this stuff. But we will not be implementing this. We don't really need to. And I think on this we can wrap it up. Just let me see if I didn't miss anything. Right, so was this dumb? Yeah, it was kind of dumb. Right, so I think we covered, so from everything which I just covered so far, I think the most important part is really PRNG, random number generators, right, and sampling, and the idea that you can study the distribution by sampling from it, that sometimes you do not know the properties of distribution, but somehow you can sample from it. And I said Monte Carlo simulation, and in particular Monte Carlo simulation of portfolio values is one such case. So we can sample and study this using Monte Carlo. And inverse CDF, again, it's another important point in this lecture, not only because I'm going to use it in assignment. You will need this in assignment, both applying CDF to random number itself and inverse CDF applying to uniform. You will need to understand and use both of them, not just for an assignment, but it's a very useful technique. And right, and finally, I think how to apply this to Gaussian is important, like, because you often need to generate Gaussian random numbers. And on that, I believe we can wrap this up.